Next talk, we'll have Remika from UCSB, who will tell us about simulations of quasiparticles on quantum devices.
Hi, everyone. My name is Remika. Thank you for the introduction. And today my goal is to make you excited about the possibility of simulating quasiparticles on quantum devices. So first of all, what are quasiparticles? They are collective many-body excitations, so many modes coming together, but they kind of behave like a particle. The first time you might have encountered this is while studying Fermi liquid theory, where you would have seen these excitations above the Fermi surface, which are long-lived and behave like a particle. But they are actually found in all kinds of systems, including quantum spin liquids and fractional quantum Hall effect. In some of these systems, the quasiparticle properties can actually be used as a probe to identify those phases. They're also very interesting because a lot of the experiments you do, like STM, NMR, they directly probe quasiparticles. So understanding them is also useful to understand many condensed matter experiments. So there exist some classical methods to study quasiparticles, but often they are limited to certain regimes where you can make approximations. So the question we asked is like, can we simulate some of them on a quantum computer, and can that give us some advantage? So I guess we have heard a lot about VQE, but I'll just give a very brief overview of what VQE is. So it's a hybrid quantum classical algorithm. On a quantum computer, you make an easy to prepare initial state, and then you apply a quantum circuit U theta to get a state, parametrized state psi theta, and you want to optimize these parameters theta using a loop between a quantum and classical computer to reach as close to the ground state of interest as possible. So usually a lot of work on VQE is done on ground states. Quasiparticles are excited states. So my research focuses on using VQE for excited states. So now the principle we saw in VQE is based on the variational principle, is that if you optimize the parameters, you would reach the lowest energy state. So what happens, how would you prepare an excited state? So one way is to use your symmetries of the Hamiltonian of interest to guide your state preparation. So let's say we have a target Hamiltonian which has some symmetry, and we understand that if we have a symmetry, then it partitions your Hilbert space into different symmetry sectors. Now, let's say your spectrum looks something like this, and there is a state of interest psi1, which belongs to a particular symmetry sector of your Hilbert space. It can be an excited state, but if it belongs to a Hilbert space sector which is different from your ground state, then if you restrict your initial state to belong to that symmetry subsector, and you demand that your unitary circuit preserves that symmetry, then your unitary circuit will not be able to take you outside that symmetry sector. So you can prepare any excited state which belongs to a different symmetry sector than the ground state, just by carefully choosing your initial state if you demand that your unitary circuit preserves that symmetry. So that's a quick way to prepare many excited states. So I'm going to illustrate with a simple example of the Ising model, which is seen here, and it has two symmetries, parity and translation. Parity is when all spins are flipped, and translation is invariance with respect to shifting by a site. And this model is commonly known to have two phases, the ferromagnetic and the paramagnetic phase. I will demonstrate in this paramagnetic phase. So when you have no coupling, it's very easy to see what the ground state is. It just all spins along, all pointing along the x eigenstates, and the first excited states would be one spin flipped. So you can tell from here that the ground state is a parity +1 state, and the manifold of first excited states are all negative parity states. Now when you have a coupling, these the first excited state gains a dispersion, and then still the quantum numbers are preserved. So now we look at how to prepare some of these excited states. So using the principle, if you want to do a ground state, you would have to start with a parity +1 momentum 0 state, which can just be all spins pointing to the right, and then for any value of J and H, for any value of coupling, you can do the VQE and you would converge to the ground state. Now what if you want to do that first excited state over there? That's a zero momentum state, but we saw that it has parity -1. So you would have to start with a state which is zero momentum and has parity -1. Now if you have odd number of sites, such a state would be a very easy state. You can just take all spins to the left and then the parity quantum number would be -1. So if you run VQE on this, you would converge to the first excited state, which is kind of interesting because this actually in the Hilbert space is the highest energy state, but then it makes your VQE very efficient. So this is just numerical demonstration of that. I start with all right and all left, and then they converge to the ground state and the first excited state respectively. And this can be a very quick method to extract the band gap of the system, like in this case. So this can also be generalized to other systems where if your first excited state and ground state belong to different symmetry sectors and you want a quick and dirty estimate of what the band gap might be, this could be an interesting way to prove it. Okay, so we saw parity eigenstates. Now what about the other K momentum eigenstates? How would we prepare them? So there, if you want to go by the same principles and choose an initial state which has a momentum K, that can be hard because a momentum K initial state is not easy to prepare. It generally takes a depth n circuit to prepare any momentum eigenstate. So there, our proposal strategy is you cannot make an initial state for single momentum, but you can construct an initial state which is a superposition of different momentum states. And again, if you demand that your unitary preserves momentum, then it is going to preserve the momentum eigenvalues of each state in the superposition separately. So in what I do, I'm going to take an equal weight superposition of all the momentum states, and our intuition tells us that that will be some kind of a localized state. And we will see in the next slide that if you start with such a localized initial state and you run your VQE, you would actually end up preparing a quasi-particle, and the quasi-particle will give you information of the entire first excited band. So let's say, so what VQE does is runs on the variational principle. So if you start with a localized state and if you try to calculate the expectation value of energy, then you would see, because these momentum are conserved quantities, you will not get any cross terms and you will just get a direct sum of each momentum eigensector. Because this is a sum and there are no cross terms, this can be minimized only if each term in the sum is minimized. So this means that each momentum must converge to the correct eigenstate, which is the lowest energy state in that sector. So you will converge to the eigenstate which has parity -1 and momentum K, which is just the first excited band. So if you run VQE on such a equal superposition of momentum states, then you will end up getting a state which is the equal superposition of all eigenstates in your first excited band. So this is just showing that in each symmetry sector, which is an intersection of parity negative and momentum K, you would have this VQE procedure take you to the correct eigenstate, and this will happen simultaneously for all eigenstates. So you can kind of utilize the power of unitary evolution, which is that it preserves each channel separately. So here is a simulation result for a simple case where we can prepare these Magnon quasi-particles, and because it is a superposition of all the eigenstates, I can extract the energy eigenvalues, so I can get the whole band dispersion just from a single run. I would just have to do some more measurements, but I can get the whole dispersion. Here I just show that it matches well with like exact diagonalizations. So that's a great, what I showed you was in the paramagnetic regime, the earlier example. You can also do this in the ferromagnetic regime, where the quasi-particles you might be familiar with are these domain walls. And so use a twisted model to kind of extract one single domain wall, and then you can do a similar method and extract the whole first excited band from one ring QE run. So to summarize, we used symmetry guided VQE for preferring excited states, and we saw that simulating quasi-particles can be interesting because it can enable you to get information on the whole excited band at once. And also simulating quasi-particles by themselves are interesting because they can explain experimental results. And I want to thank my advisor, Leon Balance, and postdoc who I work with, and thank you.